it says, consider the construction of the Koch snowflake that starts with a seed triangle that has sides of length 171 centimeters. So there's my seed. The sides are all 171. Okay. We're supposed to let M denote the number of sides on the Koch snowflake, which is always going to be the same no matter how long the sides are, right? So this one we could fill in. Remember, we discovered that that goes up by multiples of 4, by a factor of 4. So it should go 3 times 4 is 12, times 4 is 48, times 4 is 192. Say it again. 768. 30, 72. Okay, so we get that column. All right, now the length of each side always changes by a third. So that was something we discovered last class. Our seed triangle that we were investigating had sides of length 9, but the rule about how you build the snowflake is always the same. So the length of each side is always going to be a third of what it was, because that's how you build it, right? You take each side and you break it into thirds, and on the middle third you put a new triangle. So the length of each side for the new triangle is going to be a third of the original. So 171 divided by 3 apparently gives you 57. So 171 divided by 3, 57 divided by 3 is 19. Divided by 3 is 6 1/3. And it asks you to put your answers in as either an integer, which is like a counting number, right? Or a simplified fraction, so not as a decimal. So 6 1/3, you could enter, 6.3333, you could enter 6 1/3, or if you wanted to change it to an improper fraction, it would be 19/3. Either, they weren't taking 6 1/3? Okay. So 19/3. So no mixed numbers, apparently. All right, and then we divide by 3 again. 19 divided by 3 is going to be 19 over 9, right? A third of 19/3 is 19/9. And because 19 is prime, you can't reduce that. So we have 19/9. And then 19/9, take a third of that, and you get 19/27. And then your perimeter is always just the number of sides times the length of each side. So you would multiply these guys. So 48 times 19, 912. And 192 times 19/3, 1216. And 768 times 19/9. So 1621.333333, that's 1621 1/3. If you have to put it as an improper fraction, if you have a great calculator, you know how to use it, it can do it for you. I pressed math, enter, enter. So when you press the math button, that first option is arrow fraction, means change to a fraction. And most of your typical scientific calculators will have a F to D or D to F button for fraction to decimal. And then sometimes there's also a button that says like A, B, C to like, I don't know, what, D over E or something. So it'll change mixed number to improper fraction. But that's something you should be able to do also. So like if I wanted to do 1621 1/3, you multiply the whole number times the denominator and add the numerator. So it'll be 1621 times 3 plus 1 is 4,864 thirds. And then 3,072 times 19/27. And I'm just going to have my calculator do this for me. 19,000 456 ninths.
And in the example that they
Oh, yeah, that's typical. All right, so it seems like it was really in this particular one, it was really the fractions and the format of the answer that was the problem and not the. Okay, so let's look at the next one. Okay, so now we're working with the Koch Snowflake again, and we're saying we're giving you the area of the seed instead of the length of each side. So this is actually, it is different than what we did in class, but they're just trying to save you a step, right? Like I gave you the side length and made you calculate the area using s squared radical 3 over 4. Now they're giving you the area of the seed. So they're trying to take a step out, but you have to notice something about the areas of each step. So I'll show you. So we've got the area of the seed, 567 square inches. That's my Q, right? And then if you draw a triangle, oh, that's terrible. Draw an equilateral triangle. And then we take out the middle third and put an equilateral triangle on the middle third. All right, so the part I took out, I'm just going to put in dotted lines. Oh, you're right. Okay, so let's do that and that and that. Okay. So now imagine those new triangles that I just added on. Imagine if you fold them into the center, right? They would meet in the middle, and we would have triangles that look like this. So it's 1, 2, 3 triangles, and they're all the same size, right? And then if I go, all of the triangles are the same size. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So my new little triangles that I added outside, I can fit 9 of them inside the original triangle. You see that? So that means that each of these guys, right, this triangle right here, that is 1/9 the area of the seed, right? Because 9 of them can fit in the seed, so it's 1/9. And then you can, each time you do that, each new triangle you add is 1/9 the size of the previous triangles. So that is the observation about the area as you build the Koch snowflake that you need. I had you just calculate areas, but this actually makes it a little bit easier. So in step 1, we're adding 3 triangles on, right? So these 3 blue guys that I just shaded, those are my 3 new triangles added onto the Koch snowflake. And each one has area 63 square inches. And how did I know that? Because each one is 1/9 of the original. And my original was 567. So 1/9 of that is 63. So you always take 1/9 of the previous triangle. All right, and then T, that's supposed to be the total new area added. So you have 3 triangles. Each one has area 63 square inches. So that gives you the total area added. And then you have to add that 189, right? That's the area of these shaded triangles. Add that to the previous area that existed. So you have to take your 567 and add it to the 189, and you get the 756. All right, so in step 2, how many triangles am I going to add when I build step 2 of the snowflake? 12. And this is going to start growing by a factor of 4, because the number of triangles you add corresponds to the number of sides. So this would be 48, 192, and I can't remember, 768. And then because of this 1/9 deal, each time we add a triangle on, right? When I add the little triangle here, it's going to be 1/9 of the triangle it was added on to. And 1/9 of 63 is 7. 63 divided by 9 is 7. And then you do 12 times 7, which is 77 plus 7 is 84. And then you have to add that to the 756. 756 plus 84, 840. So this column was the one that we did a little bit differently. The rule here now is that S sub n is always S sub n minus 1, the previous number in the list, divided by 9. Okay, so what's 7 divided by 9? 7/9. So then you'd multiply 48 times 7/9. And you get 37 1/3. They want a simplified fraction, so I'll have my calculator do that. 112 thirds. And then add that to your previous area of 840. Change it to a fraction. 2,632 thirds. Do I need to finish? Do you kind of see the pattern? One more time, okay. On S, okay, so each S is 1/9 the previous S. So 7/9 times 1/9 is 7/81. Okay. So that is the area of each new itty bitty triangle added on in step 3. So that would be like these little guys. And because each of those is 1/9 the triangle it was added onto. Because you can fit 9 of them inside. All right, so I added on 192 of these little itty bitty guys. So you do 192 times the area of each one. 192 times 7/81. And change it to a fraction. 448 over 27. Okay. And then you have to add that to the previous area. So I'm going to add that to 2632 over 3 and change it to a fraction. And I get 24,136/27. So this whole 1/9 pattern actually makes this a lot easier than what we did in class. You just had to notice it. So those were the two that dealt with the Koch Snowflake, which was the fractal that we discussed in class. And then I know the rest of the homework may have been even more difficult because it was a new fractal. So I asked you to do the same investigations that we did for the Koch Snowflake concerning area and perimeter, but for this other fractal called the Quadratic Koch Snowflake. And this is the picture of it. So you start with a solid seed square. So instead of a triangle, you start with a square. Okay. And to build the quadratic snowflake, you take the middle third of each side of the square. So you have to divide each side into thirds. So it's like, see, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, it's 9. There's 9 little squares across. So I take the middle 3, would be the middle third. And I build a square on it and attach on each side. Oops. Right, so that would give me step 1, which looks like this. And then on every single side, you take the middle third and build a little square on it. And that's how you get this step 2. And then you just keep doing that. With every single side that remains, you put a little teeny square on the middle third. All right, so let's see what they asked us about this. So we're supposed to investigate the perimeter.
So the squares you asked, like the first square, right?
Yeah. Okay, so we were supposed to assume that the seed square had sides of length 144. So if I draw a seed square, each side is length 144. M is going to be the number of sides, L is the length of each side, and P is the perimeter. Okay, so at the start, I have 4 sides. It's just a square, right? The length of each side is 144. That was given, which means its perimeter, which is the distance around a shape, is going to be the number of sides times the length of each side. 4 times 144 is 576. All right, and then at step 1, I have to add on to the middle third of each side a new square. Okay, so I put a new square on the middle third. And now I count up the number of sides. And I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 sides. So that's where that 20 comes from, right? And the length of each side, the way I built this, the length of each side should be a third the length of the original, right? Because this piece that I pulled out was 1/3. The whole thing was 144. So if you divide 144 by 3, you get 48. So now each side is length 48. And so your perimeter is the number of sides times the length of each side. 20 times 48 is 960. All right, so we'll do one more picture and then we'll try to see patterns because drawing this gets tedious. And I should have reminded you that on the front of your packet, there's 2 pieces of grid paper so that you could draw this on graph paper. All right, so on the middle third of each side, I'm going to add a new little square. Okay, so there we go. Now, how many sides? Can I what? Erase them? Yes. Oh, yeah. Okay, I'll shade the whole thing in a second. Yeah, that one. No, that's okay. So, you're right. It's definitely going to be better if it's all one color and if it's shaded. So, okay, that's a little bit better. show you the opens? People watching this video are going to be like, I'm just watching her color. Yes, I could, but I might mess it up. Now it's way worse, right? Yeah, I could just hit undo and redo it. Here, I'll put I have an idea. No, that's not what I want. I want All right, those are the ones that aren't part of the shape. All right, so now I have to figure out how many sides there are. So let's see. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50. And I think I've done exactly half of it, right? So there's 100. Looks like multiples of 5. Yep. I could have stopped at 25 and said, oh, I've done exactly a quarter of it. Yeah. Yeah. Great. Yep. All right, so let's see. The length of each side before was 48. So the previous side that existed, let's just look right here. Like that length right there used to be 48. And I broke it into 3 pieces to build this little square on it. So I divide 48 by 3 to get the next length, which is 16. Right, and then your perimeter is your number of sides times the length of each side. So I'm going to get 1600. Okay, good. Yeah, the key was that you had to draw this well, right? You had to take the time to draw it. Yeah. Yeah. All right, so now hopefully we can see patterns. We say, oh, this looks like I'm multiplying by 5. So this is going to be 500. 500 times 5 is 2500. 2500 times 5 is 6,250. Let's just double check. $2,500 times, yeah, it's 12,500. Okay, and then these I have the same rule of a third because I'm still building it by taking each side and putting something on the middle third. So a third of 16 would be 16 thirds, and I don't think you can reduce that. 16 thirds. All right, what's a third of 16 thirds? 16 ninths. And what's a third of 16 ninths? 16 27ths. Yep. Then you multiply number of sides times the length of each side to get perimeter. So 500 times 16 thirds, change that to a fraction, 8,000 thirds. Math, enter, enter. Yeah. All right, 2,500 times 16/9. Math, enter, enter. That changes it to a fraction on my calculator. So now I have 40,000 ninths. That's a lot of ninths. And then the last one, 12,500 times 16/27. It gives me a decimal. My math lab doesn't want decimals, it wants fractions, right? So pretty much all of you have a calculator that can change a decimal to a fraction. If you don't, this is a little bit more work for you. You have to write out, you just would do it by hand like you did, back in the day. And you'd multiply the tops and multiply the bottoms. So you'd say, okay, I got to do 12,500 times 16, and that gives me 200,000 divided by 27, and then reduce it if you can, right? 200 divided by 27. I'm not sure if that reduces. I'm going to rely on my calculator. Nope, that's the best you can get. That's reduced already. Whew. All right, so the next one was, I think we're supposed to look at the area of the Koch snowflake. Not the Koch snowflake, the quadratic Koch snowflake. All right, so we do a similar investigation to what we did with the Koch snowflake, but for the quadratic one. And look at, they were so nice to do 2 lines for us. Maybe we can just guess the rules without having to draw it, right? The number of squares you add on is the same as the number of sides because you add a square to every side. So this is a factor of 5. We already learned that. So this is 100, 500. And then S is the area of each added square. So let's see, I'm just going to draw like maybe one step. So here's the first step, and the area of this square is 1,539. When I add on these squares onto the middle third, let's see if I fold them in just like I did with the snowflake. Right? I can fit 9 of them inside the original. So each of these guys is 1/9 the square it was attached to. So my original square was 1,539. 1/9 of that is 171. And then if you take 171 and divide by 9, you get 19. So then we keep dividing by 9. 19 is prime, so we'll just write 19/9. And then 1/9 of 19/9 is 19 over 81. And then T is the total area added on. So what S was the area of just a single square that I added on. And then you just have to multiply by the number that you added. Okay, so I have the area of this guy, but I added 4 of them. So I have to multiply 4 times 171 to get the 684. That's how much area I added on to the original square. And then I have to add the area of the original square to the area that I just added on, that I just attached. So 1,539 plus 684 is 2,223. Okay, so I have to do 100 times 19/9, and I get 1,900 ninths. I don't know if that can be reduced. Okay, so then I have to add that to my previous area. 2,603 plus 1,900 ninths. Get that as a fraction. And I get 25,327 ninths. Then I multiply 500 times 19 over 81. Get that as a fraction, and I have 9,500 over 81. And I have to add that to my previous area. Plus 25,327 ninths. Change it to a fraction. 237,443 over 81. Shall I leave one problem for you to think about on your own?
Yeah.
Okay. Good. So we did the first 4. There's one left. I'll let you do that. Think about it on your own. Okay, so we're going to start talking about another fractal today called Sierpinski's Triangle or Sierpinski's Gasket. In this fractal, you start with any triangle. It does not have to be equilateral, though often we draw it that way just because it's easier. And then you remove the middle, okay, from the triangle by taking the midpoint of every side. So you put the midpoint on all 3 sides, connect them, and you pull out the chunk in the middle. Okay. So you're left with this triangle at step 1. And then you do that to all the triangles that remain, right? You take the midpoint of each side, connect them, and remove that chunk in the middle. And you get step 2. Yeah, you just get rid of it. Imagine you have like a triangular hole punch and it's gone. And then you do that to all the remaining triangles. Remove the middle. So you get the middle by connecting the midpoints of the 3 sides and get rid of the middle, and you get step 3. So after a few more steps, our eyes can no longer tell the difference between one step and the next. This is the Sierpinski gasket at step 7. Step 8 would appear no different to us because the amount that you're taking out is like so small that you know, maybe just gets down to a couple of pixels and our eyes can't tell that something's been removed. Like the Koch Snowflake, no one can ever finish drawing the Sierpinski gasket. It is an abstract, theoretical, geometric object. The actual gasket is the shape that you would obtain if you could do an infinite number of iterations. Nobody can do that, which means that this is purely theoretical, but there are still some things we can know about it, despite the fact that it can only exist in our heads. Okay? It has infinite, universal, and exact self-similarity. So that means you can zoom in anywhere, blow it up, and it'll look just like the original. So what happens to the perimeter, the length of the boundary, as the number of iterations goes to infinity? What do you think? Any conjectures? Okay, it kind of depends on what we think of as perimeter. Let's look at these. Yeah, I'm thinking of that. Yeah, well, the outer perimeter stays the same, but I'm thinking of the boundary. So like now my boundary is all of this. Yeah. Yeah. And then I've got this and this and this and this. Yeah. So all the pink lines together would be the boundary. Yeah, that's just increasing. It's just getting bigger and bigger. Oops. So conjecture, perimeter is just getting bigger and bigger, going to infinity. So even though the seed of the Sierpinski gasket is not necessarily equilateral, we're going to assume that it is because it's going to make our calculations nice and easy. Okay, so here's several iterations of Sierpinski gasket. So let's assume that each side of this triangle has length 1. What's the perimeter of the seed? 3. Okay, good. What is the perimeter of this step 1 triangle?
If each of those other boundaries is the 1.
Yep. We still got 1, 1, 1. And then what are the length of these guys that we add? 1/2. Yeah. 1/2, 1/2, 1/2. So my perimeter, I still have the 3 from the outer, and now I've also added 1 1/2. So my perimeter is 4 1/2. And then my perimeter at step 2, I still have the 3 from the outer, right? I still have the 1 1/2 from this middle chunk. And then what are the lengths of each of these? 1/4, yeah. So I have 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4, 8/4, 9/4. 9/4 is 1.25. Okay, so altogether that's 4 1/2, 5, 2.25, 9/4. Yes, thank you. So 4 1/2, 6 1/2, 6.75. All right, so then my perimeter at step 3, I'm going to have everything I had at step 2. I still have 6.75, right? Then I just need to figure out all these extra little guys. Yeah, and each of these triangles has length 1/8, 1/2 the previous length. So this is, each one of these triangles has perimeter 3/8, and I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 of them. 9 times 3/8 is 27/8. And I'm going to have my calculator do that. $6.75 plus 27/8. 10.125. All right, so based on your answers to just these first few steps, right? Can you write a formula, either recursive, explicit for the perimeter or the boundary, interchangeable words there, at step n? Are they related somehow? Which means that it's not linear, right? It's not going up by the same amount each time. What else do we check? What, exponential is sort of the next rule that we would check after linear. What number do you multiply 3 by to make 4 1/2? 1 1/2. What's 4 1/2 times 1 1/2? 6.75. Oh, look, that's the next perimeter. 6.75 times 1 1/2. 10.125. Yeah. Okay, so my formula is going to be P sub n is always the previous perimeter times 1 1/2. Goes up by a factor of 1 1/2. So when you multiply by a number that's bigger than 1, does the answer get bigger or smaller? Bigger, right? Yeah, so if you had, we just finished our financial unit. If you had some money in a bank account that every day or every year or, you know, however often you got to multiply that by 1 1/2, you'd be psyched, right? Because that means it's just going to get bigger and bigger and bigger. Okay, so my perimeter keeps getting multiplied by 1 1/2 at each step, which means it's just going to grow and grow and grow and grow. So our conjecture was correct, right? My perimeter at infinity is infinity. This is some weird notation that just means P sub n approaches infinity. Right? The perimeter gets bigger and bigger and bigger. So your intuition here is totally right. That boundary just grows and grows and grows. What do you think happens to the area of this thing? Decreases. So if you could do an infinite number of iterations, if you could actually do this forever, how much area would you have left? 0. None. Good intuition. So my area, we think is, yeah, the contents, yeah, or that's a good way to describe area, yeah. The shaded part is gonna keeps getting smaller and smaller. So to investigate, look what happens at step 1. So let's consider this, 100%, right? How much remains? What fraction remains when I go to step 1? 75% or 3/4, right? Right. And then when I go from step 1 to step 2, okay, I had 1, 2, 3 whole triangles, right? And I broke each of those triangles into 4 pieces. And I threw away 3 of them. So I have a total of 12 little triangles in this picture, and I'm only keeping 9 of them, right? So if I throw 3 of the 12 away, that means I'm keeping 9/12, which is 3/4. Yeah. Right, so I had 12 little triangles, and I kept 1, 2, 3, 4, 5, 6, 7, 8, 9 of them remained, which means I kept 9/12 or 3/4 from the previous step. Same thing's going to happen here. I'm going to keep 3/4 of what I had in the previous step. So let's see, if I break these up, I have 4 times 1, 2, 3, 4, 5, 6, 7, 8. I have 36 little triangles here. I'm going to throw away the ones in the middle. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So if you have 36 and you throw away 9, how many are you keeping? 27. 27 out of 36, which reduces to 3/4. Yes. Nothing. It just stays empty. Once you throw it away, it just, like, imagine that the shaded part is paper, right? And you have a little hole punch. And so that's been thrown away. There's nothing else we can do with it. Right. Right. Yep.
So that sorry, but when you're going up by 5, quadratic snowflake, that would make it like going from triangles, because we are taking account is this triangle or square in the middle of the sides, kind of. Can you think of it that way?
Yeah.
That's the 4th piece.
Sure. Yeah, you can think of that. Good. Yes, yes, because there's 4 little triangles in there. Yeah. Okay, so let's see if we can write a recursive and an explicit formula for the area of the Sierpinski triangle at step n. So at step n, I'm always keeping 3/4 of what I had, right? So my area at step n is always my previous area times 3/4. That's a recursive formula. If I wanted to write it explicitly, I would say AN is equal to my original seed. If it had area 1, I would start with 1 and then take 3/4 of it n times. So let's relate this back to a bank account. If you have a bank account and every month or year or day or whatever unit of time, your bank account is the amount of money in your bank account is multiplied by 3/4. What's happening to the amount of money in that account? It's going down. Yeah, you're multiplying by a number less than 1, which means the amount of money in that account is getting smaller and smaller and smaller and smaller. So as n goes to infinity, the area goes towards 0. So another way of writing that would be to say the area at infinity, right? If you could do infinite iterations, which you can't, but you can sort of think about in your brain, if you could get there, you would have nothing left. All right, so here are our conclusions about the Sierpinski gasket. These are the formulas we developed today. These are also on your reference sheet that you can bring to the test. We developed a recursive formula for perimeter. And the explicit formula is definitely not worth the trouble.
You have a sheet in here that we
Yeah. Yep.
which page? Sorry.
The page 3.
Okay. Oh, I see.
Yep. We wrote it a little bit differently. We said that P sub n was P sub n minus 1 times 1.5.
Right.
Yeah. Yeah, so actually, this is wrong. That should be times. And yeah, this is an equivalent way of writing it. Maybe it's not.
Oh, you worked it.
And then we have formulas for area. 3/4 the previous oh, sorry. I should have called these A's. I changed them to A in the front sheet, but not in here. A's for area. And then after infinitely many iterations, the perimeter of the gasket is infinite and the area of the gasket is 0. That seems pretty crazy to me. You have this object that has infinite perimeter but 0 area. So this pattern pops up a little bit in nature. This is an approximation of the gasket on a shell. You can see the big triangle there, and then the middle and the little triangles. And this seems like this really theoretical, we switched from really practical financial stuff to this really theoretical fractal stuff. But this has a really good application. Cell phone antenna and all kinds of antenna, they have to have a very large boundary in order to get signals clearly, but take up very little area, right? Because we have these teeny tiny phones, right? So a fractal is the perfect thing because the more iterations you do of the Sierpinski triangle, the longer the area and the longer the perimeter and the smaller the area, right? So we actually use these things as antenna. Antenna shaped like a Sierpinski gasket is right here. So that's a picture of an antenna shaped like a Sierpinski gasket. Long perimeter, small area. They use a lot of other fractals too. Yeah, and this is one that looks kind of like the Koch Snowflake, right? And they have ones that look like the quadratic Koch Snowflake too. Those are probably more common because 90-degree angles are easier than 60-degree angles in manufacturing. So fractal antenna is based on this concept. Not just these two fractals. There are many other fractals that are used, but using a fractal as an antenna. They're used in cell phones, wireless modems, GPS receivers. So it turns out this really theoretical thing that we just decided to think about because it was interesting has this great practical application. All right, so the Sierpinski gasket shows up in another strange place. This is called the chaos game. If you start with an arbitrary triangle that has vertices A, B, and C, we roll a die. Okay, and vertex A is going to correspond to getting a 1 or a 2 on the dice. And vertex B will correspond to a 3 or a 4, and vertex C to a 5 or a 6. So here's how you play the game. You choose any point in or on or near your triangle. Any point, just choose it randomly. Put a point in there, right? Then you roll the die, and let's say we roll a 2. That corresponds to vertex A. So you now put a point exactly halfway between the point you just put down and vertex A. So you picture an imaginary line, a straight line connecting your point to vertex A. Put a point right on the midpoint there. And then pretend you didn't draw that line. That was imaginary. So this was point 1. This is point 2. So then you just do it again, but now you go from point 2. So we roll the die again, and let's say we get a 5, right? 5 corresponds to vertex C. So you have an imaginary line to vertex C, and you put a point halfway there. And that's going to be 0.3. And then you just keep playing this game. Keep rolling the dice, and keep putting a point halfway between your most recent point and the vertex that you roll. Okay. So I have a little, this will take a long time for you to see the connection to Sierpinski Gasket, but I have a little animation. If you just keep playing this game and adding more and more points, you get a picture that looks like the Sierpinski Triangle. Then you would have one point in the middle, but they would all end up clustering around here. Yeah, Emma. Nope, nothing will go in there. It's empty. Yeah.
Like I know it's empty, obviously.
Sure, yeah, sure. You could start a new one and put it in the empty square, yeah. Mm-hmm. Yeah, so it'd be like a tunnel. Yeah. Yeah, so this link is in your packet if you want to check out the little applet when you go home. That could be fun. Okay, so that's a weird place we see the Sierpinski Gasket. We have a lot of disbelief that it doesn't actually happen. I encourage you to go home and do it, right? Play the game, get a dice and play the game. It might take you many times to see the pattern, but it'll pop out eventually. All right, so here's another strange place we see the Sierpinski Triangle. It's going to require a quick detour. This is a triangle called Pascal's triangle. Can you predict the next line of this triangle? So what numbers would go if I wanted to make another row down underneath? So study it for a few minutes. See if you can predict the next line of the triangle. All right, anybody discover it? I know I'm rushing people. Any number is always the sum of the two numbers like above and to the left and right of it. So like this 6 came from the 3 and the 3, right? And this 4 came from the 3 and the 1. So if I wanted to write out the next row, well, it looks like I always have 1s on the outside. So I'll put a 1 here and a 1 here. And then each other number in the row is the sum of the two above it. 1 and 7 is 8. 7 and 21 is 28. 21 and 35 is 56. 70, 56, 28, 8. There are tons of patterns, and mathematicians have studied this triangle like since I think Pascal was around in the 1700s, but this triangle existed even before him. I'm going to show you one pattern just to, I usually show several, but we're running a little short on time because of the homework review. I'm going to show you one pattern, my favorite pattern. I'm going to draw lines diagonally through this thing, and every time I draw the line, I'm going to add up all the numbers that the line went through. Okay, so here's my first one. The only number that line went through was 1, so I have 1. And then my next one, the only number that I went through was 1, so I get another 1. And now I went through a 1 and a 1, so I get a 2. And then I have 1 plus 2, which is 3. And then this line went through 1, a 3, and a 1, which adds up to 5. I'm hearing several people call out the name of a sequence that this reminds them of. Right? So now I go through 1, 4, 3, and 1. 1 and 4 is 5, and 3 is, oh no, it just doesn't go through the 1. 1 and 4 is 5, and 3 is 8. Yep. All right, and then the next one, we have 1 plus 5 is 6, plus 6 is 12, plus 1 is 13. That is the Fibonacci sequence. 1, 1, 2, 3, 5, 8, 13. All right, so that was our little detour. This is Pascal's triangle. There's a gajillion patterns in there. One of them is that you can find the Fibonacci numbers. Okay. Let's relate it back to Pascal's triangle. Here is, I'm sorry, we're going to relate it back to the Sierpinski gasket. This is Pascal's triangle. I want to color, if you divide a number by 2 and the remainder is 0, what special kind of number is that? A number that you can divide it by 2 and have no remainder. 2 goes into it evenly. Those numbers have a special name. You probably learned it like second grade-ish.
Even numbers?
Even numbers, yes. If you divide a number by 2 and you have no remainder, 2 went in evenly, that's an even number, right? And if you have a remainder, right, if you have a remainder of 1, what kind of number is that? Odd. Okay, so I want you to color the evens one color and the odds another color. You can just shade them, yeah. All right, so just another surprising place where we see this fractal pop up. Why do you think that this fractal has something to do with even and odd numbers? Right? What the even, if you separate it into evens and odds, you get this pattern. Any ideas why? Yeah.
Whoever created this really hates odds.
Why? Odds?
I think it makes sense.
Why? Why do you think that evens and odds, shading evens and odds, created this pattern where, like, you get this triangular pattern? Oh, no. Yeah, so okay, think about like a small spot. Like, let's look at just the bottom of this one triangle here. So these two numbers are even, right? And to get the number right below it, you add them together, right? What's an even plus an even? Also even, right? So that's why you get these narrowing triangles, because we have a row of evens here, and when you add two evens, you get an even, right? So we keep getting smaller and smaller and smaller and getting evens in this triangular formation, right? And then, and how else can you get an even? An even plus an even, two odds, yeah. So two odds can make an even. So that's why when you have a whole row of odds, the next row is all evens, and then you get this arrow narrowing thing. So it has to do with the rules about adding evens and odds, why these triangles pop up. It's the structure of the triangle with the adding the two to get the one below. Interesting? A little bit? Okay. Okay, that's it.